Welcome back, everyone. So we are in chapter 4 now. We're going to start what we call integration, which is going to be the second main topic of calculus. So we've spent quite a bit of time discussing derivatives, which we built from limits, the limit of the slope of the secant line. And now we're going to look at something called integration. And at the end of this chapter, or towards the end of this chapter, we're going to connect the ideas of differentiation and integration. So today what we're going to start off with is anti-differentiation. So the process of reversing differentiation is called anti-differentiation. So what we're going to do is we're going to start with functions that are themselves derivatives of some kind. We're going to try and go backwards and figure out what the original function is. So up at the top here, suppose we knew f of x was, or f prime of x was equal to 3x squared plus 4x plus 2. And we want to know what f of x was. So we could take each piece and kind of work backwards here. The nice thing is that our function is a polynomial. So we know that the rule for differentiating is the power rule. So what we need to figure out is what does the power rule look like in reverse. So we can take this term by term. So 3x squared, if we go backwards, is going to have to give us x cubed. X cubed has to be the power of the previous term. And if we notice here, we have a 3 as our coefficient. So if that's going to come back up as the exponent, then x cubed is actually the antiderivative of 3x squared. So let's note that we're looking for f of x. So for 4x, we know that we're going to need an x squared term, and in order to get 4x when we differentiate, we'll put a 2 as the coefficient of that term. So 2x squared's derivative is 4x. So note all of these you can check by simply differentiating the expression you end up with. And then a constant term is easy, it's going to be linear. So we have x cubed plus 2x squared plus 2x. So this is what f of x might look like. But what we're not accounting for is when we differentiate, if we have a constant of some kind here, so maybe 10, maybe 100, maybe 1,000, whatever that number is, that constant becomes 0. So this unknown constant that may or may not exist, we denote with the expression plus c. So we add this on because there could be some sort of a vertical shift. So note this accounts for a vertical shift, which has no effect on our slopes. So if we were looking at a graph here of our function, and we added a plus c on the end, no, we can shift this anywhere vertically, and the slopes remain the same at every x coordinate. So there's no difference in slopes. So what this is telling us then is that since c can be any number, there is an infinite number of possible functions, which means that our antiderivative is not like a single function, but it's what we call a family of functions. So that's where we're going to get our notation for below. So antiderivative, the antiderivative f of a function f of x is the family, and we could think of it as set if we wanted to also, of functions such that the derivative of capital F plus c is equal to little f of x. All right, so this is going to be typical notation here. So know what we're saying here is that f prime of x is equal to little f of x. So where capital F is that antiderivative expression. And the constant c is called the constant of integration. So when you see antidifferentiation, that is equivalent in some ways to this word integration. So there's really two words that we're going to use, where antidifferentiation is really more the specific case that we're working on today, whereas integration is going to have a couple of different possible representations. So we'll note down here, in general, an antiderivative is just an antiderivative, not the antiderivative, because we have that plus c, so there's not necessarily a definite one. We can get the exact antiderivative if we have more information. An antiderivative must have the plus c. Okay, so let's find the antiderivative of the function f of x given here. So here we want to find capital F. And so we need to employ some notation here. And we're going to discuss that notation in a little bit. So if we kind of scroll down here, we've got this differential form. So I'll just put it here to note how we're going to write antidifferentiation. So we'll note that if dy dx is equal to f prime of x, right? Those are equivalent notations. What we're going to do is we're going to blend these notations and we're going to rewrite them as dy equals f prime of x dx. And note y is simply f of x. So this dy I could write as, df of x if I wanted to. But we'll just keep it as dy using that typical differential notation. So if I want to solve for f, which is y, the way we're going to write that is we're going to put this little squiggly s symbol here. And this is the integration symbol for the moment. Okay, so we'll discuss more what the s means once we get to further forms of integration. But what we're going to do is we're going to treat that s symbol just like we would treat the ddx symbol. It is an operator. It is telling us, in this case, to anti-differentiate, whereas ddx, of course, tells us to differentiate. So that little symbol there is just telling us you're going to find the antiderivative of this expression. So the antiderivative of 1 dy is just going to be y. So our left-hand side, the integral of dy is just the integral of 1 dy. So that's just going to be y, right? Because if we just have y, the derivative of y is just, the differential of y is just dy. But on the right, we're going to get our expression in terms of x. So the integral here is going to be f of x plus c. And by integral, I just mean antiderivative. So integral, antiderivative mean equivalent things. So we're going to use this notation. So let's go ahead and scoot over here. So if that is little f of x, then we want to find the integral of 1 plus 6x over x cubed dx. So that's what our expression is going to look like. And this is going to equal our dy. So, but we don't have to write that left-hand side. We can just write the integral expression. So now we've got a much more complicated expression. It's much harder to kind of see, what are we going to do here? And so part of this chapter is going to be developing methods for evaluating these. This one, however, has a very simple approach that is going to be very common. If you have a monomial term in your denominator and a multinomial or polynomial expression in your numerator, one trick you can use is to split it up. So I'm going to split this as 1 over x cubed plus, and then 6x over x cubed will cancel in x. So we'll have 6 over x squared. And now we can work backwards by using our power rule because we've got x to the negative 3 plus 6x to the negative 2. You could leave it in the fractional form if you wanted to. So again, either form here. And now we're just going to reverse the differentiation process. So x to the negative 3, if we go backwards, means we're going to have x to the negative 2. And then for x squared, we're going to have x to the negative 1. And now we need to kind of play around with what are the coefficients we need to give us the correct derivative. So clearly the coefficient on the x cubed is 1. So we want it to be 1. So if I differentiate this term, I'm going to have a negative 2. So to offset that, I'm going to put the reciprocal of that power, which again, we can check by differentiating to show that that's going to be equal to 1. For my second term, I've got a 6. So for that, we're going to have to look here. So we've got x to the negative 1. We want it to be positive 6 when we differentiate. So it's going to be minus 6x to the negative 1. And then again, plus c. And again, you could rewrite this in fractional form if you wanted to. Put the x squared in the denominator of the first term and the x to the negative 1 as over x in the second term. But either expression is perfectly fine. All right. So now let's add in some trig functions as well. All right, so not everything is going to be power rule, obviously. So if we want to find the antiderivative of 4 sine x plus this expression on the right, again, we'll split the monomial term, split the fractions into 2 separate monomial terms. So we'll have 2x to the 4th when we divide the x out of 2x to the 5th, minus, and then rad x over x is going to be the same as x to the negative 1/2, or 1 over rad x, however you want to write it, dx. So this is going to be what we want to anti-differentiate. All right, so then we'll go term by term. For sine x, it's going to be pretty simple. We just need to figure out what the antiderivative is, but we know that the derivative of sine alternates between cosine and sine. So this is going to be 4 cosine x, and then we just have to think about plus or minus. So if I differentiate 4 cosine x, I get negative 4 sine x, which I don't want. So that means this is going to be negative 4 cosine x. And again, you're always going to be checking to make sure, does the derivative match up with the original integrated expression? Okay, and then 2x to the 4th is going to give us x cubed. And we need a 2 as our coefficient after differentiating. So 2/3 then is going to have to be our lead coefficient. Again, we can check that. Oh, whoops. I'm differentiating here. Is x to the 5th. Always remember you're going backwards. So that should be 2/5 x to the 5th. And then minus, if we do the reverse power rule of x to the negative 1/2, we'll get x to the positive 1/2. But again, we want a coefficient of 1. So we're going to need to reciprocate the power as the coefficient. And that will give us our x to the negative 1/2, all plus c. So a lot of 4.1 is just going to be kind of getting familiar with this reverse power rule and then some trig expressions. So sines, cosines, you might see derivatives of tangent or derivatives of secant, etc. So secant tan, secant squared, negative cosecant squared, etc. So a lot of varieties of those derivatives that we've learned in the previous 2 chapters. Okay. So those are our first 2 examples. So if we move on here, we've got a couple more examples. We've got a differential equation that we're going to discuss. The differential form is here, which is just kind of more of an explanation of where this new notation is coming from. And then we've got more examples. So let's go ahead and look at the differential equation. So when we're looking at an equation given where we know the derivative, that equation is simply called a differential equation. And differential equations is a huge field of mathematics. It covers all sorts of different areas and applications. And so what we're going to look at is what we call initial condition differential equation problems, or first order differential equation problems. but it does get much, much more complex where it's an entire field of study on its own. So we'll look at our example here, which will be kind of an introduction to the differential equation. So note, with these problems, we're often interested in finding the original function, obviously what we've been doing, but we're going to be given some initial conditions, which means we're not going to have an antiderivative that is a family of functions. We're going to have an antiderivative that is the exact original function. And that's the goal of differential equations, is to figure out the original function or the original values by using this information about slopes. So we've got our differential equation here. So f prime of x is equal to 8x cubed plus 12x plus 3. And we know that at x equals 1, our function is 6. So if we know this piece of information, we can actually figure out this function. So let's go ahead and integrate. So the integral of f prime of x dx is the integral of 8x cubed plus 12x plus 3 dx. So let's go ahead and anti-differentiate. So we're going to have x to the 4th, which means we need a 2, plus x squared, and we need 12, so we're going to make that a 6, plus 3x plus c. And so this is just going to be f of x. Let me write that a little nicer. All right, there's f of x. And now we know that f of 1 is equal to, well, that's going to be 2 plus 6 plus 3, because the 1 doesn't change any of those coefficients, plus c. And that's going to equal 6, which means now we can actually solve for the exact c. So we can see that the 6 here will cancel. We can subtract 2 and subtract 3, which means we're going to subtract 5. So then c is equal to negative 5, which means that f of x is equal to 2x to the 4th plus 6x squared plus 3x minus 5. And that is our original function. So this is going to be the goal for differential equations for us, is to find that original function if possible. And of course, things will get more complicated as we go. All right, so down here is kind of the previous explanation that I mentioned of going from that derivative notation as a ratio into this product expression where dy is equal to f prime of x times dx as opposed to dy divided by dx is equal to f prime of x. We call this differential form, the differential form, because of course we've got our two differentials here whose ratio we know as the derivative, but these are these infinitesimally small changes in x and y over the function. And so we call this expression here an indefinite integral. All right, so this is what we call an indefinite integral. And what that means is that there is going to be also something that we call the definite integral. Okay, so this is going to be kind of the main focus of the chapter, whereas the indefinite integral, what we work on today, is really the process or the style of computation that it's going to look like. But definite integral is going to be the same thing, but it's going to be across a domain. So we're going to have these limits that we write up in the bottom portion and top portion of that S symbol. And this, as opposed to being a function, is going to represent a number. And so we're going to have to spend a bit of time figuring out why that is and what that number represents. So for now, though, we're only going to worry about these indefinite integrals. And the indefinite part is because we don't define the domain here when we're evaluating it, right? So the domain is kind of separate to the process that we're working on, which means that we do have to be careful because we could have functions whose domains are, going to contain discontinuities. Okay. All right. So let's go ahead and stop there, and then when we come back, we'll work on those remaining examples. So if you have questions, definitely come by the office hours. Otherwise, until I see you next time.